A rotating rigid bar. A rigid bar with mass capital M, length capital L, and a uniformly distributed positive charge Q is free to pivot about the origin in the presence of a spatially uniform electric field EJ hat as shown in figure. So we have uniformly distributed positive charge and it's free to pivot about the origin in the presence of a uniform electric field in j hat direction. Assume that the electric forces are large enough for gravity to be neglected, so we're not considering gravitational field. Part A, write the potential V as a function of y due to the electric field as a function of y using the convention potential at 0 is equal to V0. At y is equal to 0 is V0, where V0 is a constant to be determined. Okay, so let's start with this. The relationship between the electric field and the potential is electric field E is minus the gradient of the potential. And we can go from electric field to potential. If you would like to know the potential at position y, v of y minus v at y is equal to 0 is minus the integral from 0 to position y, electric field dot product with displacement dy. Now if I substitute for the electric field Ej hat, it's a spatially uniform electric field, Ej hat. For dy, I substitute dy vector is dy in j hat direction. J hat dot j hat is 1, so this is going to give me minus e times dy. dy integrated from 0 to y will give me just y, so this is going to be minus e times y, and I know that potential at y is equal to 0 was given to me as V0. So what do I find? So I find that V at position y is equal to V at position y is equal to 0 minus EY, because this difference is equal to minus EY. So I take V of 0 to the right hand side, and this gives me, for the potential spatial dependence, V as a function of y to be, for B at y is equal to 0, I substitute V0. So this is V0 minus EY. All right. So that's the answer to part A of the problem. Now let's move on to part B. Determine the electric potential energy U of the system as a function of theta and V0. Note that the potential energy is integral V dq. So here we have this uniformly distributed charge on this bar. So we're going to integrate over the potential dq product from y is equal to 0 to y is equal to y max, which is L cosine theta in this case, to get our answer. All right, so in part B, we are considering infinitesimal charges dq on this bar, and the bar makes an angle theta with respect to the vertical axis. Electric field is uniform in j hat direction, and in this triangle here, if I go to a position x from origin to position x and the position y on the vertical axis, this is the length L, and I'm choosing a point, an infinitesimal charge dq on this axis, And you can see that this angle theta basically will appear also here. So that's this angle theta here. And if I consider how to write this dq, first I need to determine the charge density. Charge density, this is a one-dimensional object, so this is basically linear charge density lambda, which is the total charge q divided by the total length of the bar L. And dq will be the infinitesimal charge dq will be equal to lambda times dl. That is basically an infinitesimal length. Now I see that there is a relationship between L and Y. Y is equal to L cosine theta. So dy is equal to dl cosine theta. The angle is not changing here, so it's or I'm considering it for a fixed angle theta here. So the relationship between dl and dy is that dl is equal to dy divided by cosine theta. So and now I know how to write dq. dq is lambda dl, which is lambda times dy over cosine theta, where lambda is capital Q over capital L. So that's what I'm going to do now. I write dq. dq is equal to lambda, which is capital Q over capital L, dl, which is dy over cosine theta, dy over cosine theta. And the maximum value y can have is capital L cosine theta in the integral I'm going to write, because that's basically the end of the bar here. So this is going to correspond to capital L cosine theta. So here I have L cosine theta as the maximum value of y. All right, so the potential energy then is U is equal to integral from y is equal to 0 to y is equal to its maximum value, y max, potential V of y multiplied by dq. Remember, potential by definition is the potential energy per charge. So this will be integrated between 0 and capital L cosine theta. The potential as a function of y, I know from part A, is this constant V0 minus EY. The dq is capital Q over L, capital L cosine theta dy. So capital Q over L cosine theta comes out of the integral. Capital Q divided by capital L cosine theta. Now I'm performing the integration. So here I have V0 times dy. That integral gives me V0 times y. And then this integral minus EY dy will give me minus EY squared over 2. Y squared over 2. And this will be evaluated between y is equal to 0 and capital L cosine theta. All right. So if I substitute the limits, I will obtain V0 capital L cosine theta minus EY squared over 2. So that's E over 2 L square cosine square theta multiplied by capital Q over capital L cosine theta. So this allows me to write the final answer. U is equal to Q times, because I will have a cancellation of capital L cosine thetas, one of the capital L cosine thetas here. Here this term disappears, and here I get rid of the square. Q times, capital Q times V0 minus E over 2 capital L cosine theta. So I have obtained the potential energy as a function of the initial potential V0 and theta. That was basically what I was asked to do in part B of the problem. In part C, for what value of V0 does the potential energy vanish when theta is equal to 0? Okay, let's check. I know the potential energy is a function of theta, so let's substitute theta is equal to 0 degrees. Cosine 0 is equal to 1, so this will make it V0 minus EL over 2 in the parentheses. So capital Q times V0 minus EL over 2. And I want this to be 0, this potential energy to be 0. That's basically my reference in the definition of potential energy of the system. So this tells me that what I call V0, the constant value of the potential at theta is at y is equal to 0, is EL over 2. So with that, I make sure that the potential energy at theta is equal to 0 corresponds to 0 potential energy. Let's look at part D. If the bar is released from rest, so it is released from rest, at the position theta is equal to 90 degrees, what is the angular speed? So I want to know the angular speed of the bar as it passes the position theta is equal to 0 degrees. So you can see that this is released from rest at theta is equal to 90 degrees. So theta is equal to 90 degrees is here. And then it's going to rotate until theta becomes 0 degrees. So we would like to know the final angular speed. Remember that the gravitational force has no effect here. The force that we're considering is the electrical force due to this uniform electric field. Okay, so let's see. The potential energy of the bar U at theta is equal to 90 degrees is going to be, when I substitute for theta 90 here, cosine 90 is 0, capital Q times V0. So this is capital Q times V0. And the potential energy at theta is equal to 0 degrees is 0. That's what I have made sure in part C of the problem. Now, as the bar rotates, the potential energy will turn into kinetic energy. The change in potential energy plus change in kinetic energy is equal to 0 because there is no dissipative force in this problem. the change in kinetic energy will be equal to minus the change in potential energy. So let's write minus the change in potential energy. Initial angle is 90 degrees, final angle is 0 degrees. So potential at 0 degrees minus potential at 90 degrees. This is minus 0 minus Q times V0. So that will give me Q times V0. So this is equal to capital Q times V0. So the change in kinetic energy, delta K, now initially this was at rest. Finally it is rotating, so it has rotational kinetic energy. 1 over 2 moment of inertia I omega final square. This is equal to minus the change in potential energy, which is Q times V0. So I find that the final angular speed should be equal to 2 capital Q V0 divided by moment of inertia I square root. The moment of inertia of this bar for rotations about its endpoint is not given to me, so I have to determine what the moment of inertia is. The moment of inertia is by definition integral r squared dm for a continuous mass distribution. If you consider the bar here, at a distance x from the origin, I'm at this position x, and if I look at an infinitesimal length dx, the mass of this portion will be total mass m divided by total length L times dx. Mass density, linear mass density times dx for a uniform mass distribution. The moment of inertia for rotations about this axis, this is my pivot point, is integral from x equals 0 to x equals L. The maximum value of x here is L. R squared, so that's the distance from the rotation axis to the mass, infinitesimal mass, that is x. So it is integral x squared. For dm, I substitute capital M over capital L dx. So this gives me capital M over capital L x cubed over 3, x cubed over 3, which will be evaluated between 0 and capital L. So I find the moment of inertia to be capital M L squared over 3. So that's for rotations about the endpoint. Now, if I note that in part C, I have found V0 to be E L over 2 for zero potential energy at 0 degrees. This is from part C. Then I can write my final angular speed, omega final, square root 2qv0 over I. So I have 2 capital Q. For V0, I substitute EL over 2. For the reciprocal of moment of inertia, I substitute 3 divided by capital M L squared, and this to the power 1/2. Now you can see that 2's will cancel, and one of the L's will disappear, and I will be left with the final angular speed, omega final, 3EQ, 3EQ over ML square root. All right, so we're going to leave part E for the next video. So in this problem, we have considered this rotating bar. So this electric field tells us that there is a positive charge distribution here and a negative charge distribution here. This is a positively charged bar. You can see that this will try to rotate to close this angle theta here, which is with respect to the y-axis, so that these charges will line up with the electric field. So there will be a torque acting in this direction. So we want to know the potential due to the electric field, uniform electric field, which is in j hat direction, using the convention that for theta is equal to 0, we have a potential V0. So we did that by looking at the relationship between potential and electric field. E is minus gradient of V, or V of y minus V0 from potential at y with respect to potential at y is equal to 0 is minus the integral from 0 to y E dot dy, the path integral, and that gives us potential as a function of y, V0 minus EY. In part B, we determine the potential energy of the system as a function of theta and V0. For that, we do this integral V dq, where dq is lambda dl, where lambda is capital Q over capital L, uniform linear charge density, and dl times lambda is equal to dq, and y is equal to L cosine theta, so dy is dl cosine theta, so dl is dy divided by cosine theta. And writing for dq, capital Q over L, dy over cosine theta, and noting that the maximum y value here is capital L cosine theta, we obtain this integral 0 to y max v of y dq, and this gives us our answer for potential energy. If we set theta is equal to 0, cosine 0 is 1, we obtain, by requiring that this potential energy will be 0, V0 should be equal to EL over 2. And if we release the bar at the position theta is equal to 90 degrees, here, it's going to rotate to close this angle. And we want to know the angular speed as it passes the position theta is equal to 0. The easiest thing to think about is the change in the potential energy. Theta is equal to 90 degrees. We have potential energy QV0 because cosine 90 is 0, so this will disappear, QV0. And potential energy at theta is equal to 0 is 0 by letting V0 equals EL over 2. So delta U plus delta K is equal to 0. Why is that? Because we have a conservative electrical force. There is no friction or any other non-conservative force in this system. Therefore, we have conservation of mechanical energy. The change in kinetic energy is minus the change in potential energy, which is QV0. And the kinetic energy is purely rotational. The bar will not translate. It is pivoted at its end point here. So it's going to rotate. So we have 1/2 I omega final square minus 1/2 I omega initial square, but omega initial is 0. It was released at rest, is equal to QV0. So we find omega final to be square root 2 QV0 over I. For V0, we substitute EL over 2. For I, moment of inertia, we can find using integral R squared dm to be capital ML squared over 3. We substitute this, and we obtain the final angular speed as it passes the position theta is equal to 0. So that's basically going to be its final angular speed as it passes theta is equal to 0.